Alright guys, today let's talk about what we have for today. This is actually the first class we are having in Maths 120. So the course title is Calculus, while the course code is MTH 120.1. Okay, and everything we're going to talk about in this course is centered on calculus. Okay, so we have topics to be covered. The topics are, the first one is the real valued or real value functions. The second one is the graphs of functions. Graphs of functions. And after discussing graphs of functions, we'll now talk about limits and continuity of real valued functions. Then as soon as we are done with that, we will discuss the introduction to differentiation. Introduction to differentiation. Another introduction to differentiation, in fact, the main topic for this section is differentiation, but we're going to start with the introduction to differentiation. We'll see various methods of solving differentiation problems. Okay, now after that we will go to integrals or integration in general. Integration, then after that we'll talk about definite integrals. And at the end of all these topics, we are going to do question review. Then prepare ourselves for the exam. Now, there is no way you will follow all our courses and our classes without having an A in your exam. It is not possible. Insofar as you're following us, you definitely have good grades. Okay? Now, I would not bother myself with the real valued functions because we've already talked about that in our MTH 110 algebra and trigonometry, where we discussed the types of functions, the basic operations in functions. We also talked about inverse of a function, composition of functions, and so on and so forth. So I assume we've done that. If you need more information on the real value function, you can go to the course on MTH 110. While the graphs of a function, I would actually skip this for now. I'm going to skip this for now because it has little applications in your exam. Okay, now where we will delve more into the graph of functions is where we start solving problems. There is no way you understand the real value function that you will not understand graphs of functions. Okay, so I'll skip that and go into the limits and continuity of real valued functions. So that will be our focus for today's class. And if we can't finish it up before the end of the class, we are going to extend the class till probably tomorrow or in our next class. So the topic for today is limits and continuity. Limits and continuity of real value functions, or simply put, limits and continuity of functions. Okay, now our main focus in this series is to ascertain the behavior of some real valued functions as they approach a given fixed number as they approach an infinitely large number. Sometimes you call it as they approach infinity. So we will introduce several techniques that can be used to achieve this in this class. So first, let us approach the concept of limits from this perspective. So discussing what limits are first, because understanding what limits are will give us a clue into what the mathematical statement will look like. So limits simply entail analyzing the behavior of functions. Let's say functions like f of x, okay, as it approaches a particular fixed number. We say f of x equals a function as x approaches a particular number. Let's call the number a. But not getting to that exact number. So if the number is, let's say 2, we are going to analyze the behavior of the function of x. That is, the independent variable is x. So the function of the independent variable x, as it approaches a particular number, let's say number 2, let's say 2, from either the left or the right. So that is actually what we do when it comes to limits. We want to check the behavior of a particular system or a particular function as it approaches a particular number without getting to that number. Okay? Now, conventionally, like generally, what limits means? Limit is seen as a point which is not possible which is not safe to go beyond. Okay? It's a point where you just try as much as possible not to get to, because when you get there, it might be disastrous. Okay, now it could also be seen as an amount or number that is highest or the lowest number allowed. And we can have different applications of limits. So let us take an example: swimming pool. One of the ways limits have applications is in the swimming pool. So let's say swimming pools, for example. Most times when you go to the swimming pool, you see depth limits pasted or inscribed boldly close to the swimming pool. What this is for is actually to check or to put a check on how the swimmers behave around the pool. Do you understand? So beyond which you, the swimmer, might be in trouble if you ignore. Now, how about the safety precautions we see in most companies? These are also limits to check people's activities around the workplace. And of course, for those of you like me who like traveling or adventures, you are going to know that most highways have speed limits. You might be in danger if you ignore all these signs. So these and many more are practical examples of limits. You see that almost everything in mathematics find applications in real life scenarios. Now, back to what we have for today's class. Let us consider an example to illustrate mathematically what limits is all about. Okay, for instance, if our intention is to study the behavior of a particular function, let's see this f of x now is equal to 3x minus 2. Now I want to observe the behavior of this function 3x minus 2 as it approaches a particular value. So in this case, this a is now equal to 2. So as this function approaches a particular value 2, see, most times, in fact, about 60% of students find limits and continuity very, very difficult based on the misconceptions they have over the years. But in the real sense, limits is very, very easy. Is that okay? So follow me closely as I show you how this is done. If our aim, if our intention is to check how this function behaves when the independent variable x tends to 2, Remember, it approaches 2, but it must not get to 2. That is our major focus. Is that okay? Now, what this is trying to tell us is that we should look for values that is approaching 2 from both left and the right. So let's say we have x. Let's make a table, x and f of x. So if this is our table, and the first one here, we have 1.9. We have 1.9 here. So we have 1.99. We have 2 points. Okay, we have 1.999. If we have 1.999, and we also have 1.9999, then 2.0001, 2.000001, we have 2.01. Now let's say these are the functions we have, okay? Now, you realize that we add some values approaching 2, but as soon as we get to a value very close to 2, we stop and jump to the other by having 2.001, 2.01, and so on and so forth. So, invariably, what we're asked to do is, anywhere we see the value of x in the function 3x minus 2, we should put 2 inside. Okay? So, if you do that, we'll have something like this, 3.7. We'll have 3.97. We have 3.997. Okay? We have 3.9997. Okay? 3.997. Okay? We have 997, 3.9997. Then if we jump to and we put x equals 2.001 into the function 3x minus 2, we have something like this. We have 4.0003. We have 4.003. We have 4.03. Okay, so we have been able to tabulate our values. Whenever we see x in 3x minus 2, let's put 1.9 there. Whenever we see x in 3x minus 2, we put 1.99, and so on and so forth. So we're able to compute the value of f of x for this particular function, and this is what we have. So one of the things you will observe here is that as the values of x approaches 2, okay, the value of the function f of x, in this case 3x minus 2, gets closer to the whole number 4. That was the reason. You realize that between these two values, we have smaller values. But out of those smaller values, we have a value 2. Okay? So as the value of x tends to 2, the value of f of x tends or gets closer to the whole number 4. Is that okay? So, by definition, what we simply have is, so by definition, we have that the function f of x gets closer. Okay, if we make f of x closer to a particular number, okay, if we make f of x closer to a particular number, let's say the number is L. Let's say, by definition, if we make the value of f of x closer to a particular number, let's say L. L is the number. By choosing x very close but not equal to the number itself, like we saw in this table over here, then we say L is said to be the limit of the function f of x as it tends to a number, let's say a, that is, as x tends to a, f of x is equal to L. So mathematically, we can write this as the limit of f of x, okay, as x tends to a is equal to L. And this is just the mathematical expression of what we have in this illustration over here. So that is just what we have. So I'm sure you understand now. Now let us take note. I've said this earlier, but for emphasis sake, note that L is called the limit. L is called the limit, and A, the number A, is called the limit point. The limit point. So it is that point that we don't want to get to, because once we get there, there is disaster calling. Do you understand? Okay, now let me clarify this concept of right hand limits and left hand limits. This particular concept gives students issues most times while dealing with limit problems. It gives students tough time. So let us talk about the right hand limits and left hand limits. So I'll shorten it using RHL for right hand limit and LHL for left hand limit. Okay, now this simply shows the direction from which the independent variable x approaches a particular number a. So what we know, in physics we talked about scalar and vector quantities. We said vector quantities have direction, while scalar quantities don't have direction. When we are dealing with the direction of a particular quantity, we talk with respect to vector. But the other way around, if you're just dealing with how the quantity looks like, we talk about scalar. I'm sure I'm correct. Yes. So the same thing is applicable here. When we want to consider the direction of approach of the independent variable as it tends to another number, let's say a, then we consider both the left hand limit and the right hand limit. So the right hand limit approaches from the right, while the left hand limit approaches from the left. It's as simple as that. So in the example we considered above, that we said that f of x, so let's say for instance, we had earlier that f of x equals 3x minus 2. That's what we had. So therefore, we have the limits of 3x of the function 3x minus 2 as x tends to 2. So as x tends to 2, we have that f of 2 will now be equal to 3 into 2 minus 2. Therefore, this will give us 6 minus 2. Of course, 6 minus 2 equal to 4. So in this particular problem, our focus was not on the direction x is tending from. Our major focus was the fact that x tends to 2. So anything we are doing, we are making sure that we don't have that value of 2. But this is independent of the direction from which x approaches a. That is this problem now. is independent of the direction. So we are right to conclude that for a limit to exist, take note, for a limit to exist, as x approaches a particular number, let's say a, the right-hand limit and the left-hand limit must be equal. What then is the right-hand limit and the left-hand limit? Let me show you using this notation. So we have that the limit as of f of x as x tends to a, I'll use negative sign or negative bar on top of a to show, to differentiate left-hand limit from the right-hand limit. So the limit of the function, any function whatsoever, f of x, as x tends to a particular number a from the left, which is differentiated using this negative sign on top, is definitely equal to L. And to differentiate this limit from the other one, from the other on the right hand side, let us use L1. Okay? Then limit of f of x as x tends to a as well from the right, so let us use plus to denote that, is equal to L2. So we say that this over here is the left hand limit, while this over here is the right hand limit. And what is the major difference between the left hand limit and the right hand limit? It just shows the direction from which it is approaching, from which x is approaching the particular number a. It's as simple as that. Okay.